General relativity, step by step. Last time we evaluated the Riemann-Christoffel curvature tensor in circumstances appropriate for a gravitational wave, with time in this slot here and this slot here, and gamma and nu upstairs and downstairs being free. And we worked out that there were only 4 non-zero components, and here they were. We've got the xx, xy, yx and yy components, multiplied by alpha and beta, times this thing called v here, which I'll refer to later. Okay, so why did we want this? Well, what we wanted to work out the tidal acceleration of small particles close to a reference particle. So if I've got my particle here and small particles near it, I wanted to work out my tidal acceleration caused by the curvature of space-time when a gravitational wave passed it. And they were all doing all sorts of different things like that. And so the formula that we developed was d2n by dt squared, component, well, let me get it right, component gamma. I use gamma because that's the upstairs index here, equals minus r gamma t nu t n nu, where n are these separation vectors here. That's the separation vector between our reference point here and the particle in free fall that we're interested in. Well, this is great because we know this now. We know what the Riemann-Christoffel curvature tensor is. It's just got 4 non-zero terms which are down here. So I can work on this. I'm going to write a for the acceleration, and bearing in mind that this is the 3 acceleration that I'm interested in now. Component gamma equals minus r gamma t, and then I'm just going to expand it a little bit. I'm going to put x, t, n, x. I guess it's still a minus, isn't it? Or it's plus minus r. Gamma matches that gamma there. We've got a t, y, t, n, y. So this one here is the nu equals x, and this one here is nu equals y. And we're summing over nu. So that tells us that the x component of the acceleration of these particles here equals minus r, and now I'm putting gamma equals x into this formula. I could just copy it down. Gamma equals x, txt nx plus, I'll put the brackets in, minus r, gamma equals x, t, y, t, n, y. And of course, y is the same thing, but substituting gamma equals y. Minus r, gamma equals y, txt nx plus minus, bracket should be there, r. That's got to be a y to match that y there. T, y, t, n, y. Well, that's great. We can actually work out these things now because we've got them all up here. We've got all our formulas here. There we go. We've got all the formulas up there. Yeah. So I'm going to use those. I can't quite put them all on the same page. Sorry, my computer is glitching out here. What I want to do is to take these 4 non-zero components of the Riemann-Christoffel tensor, and I've got nice expressions for them. I'm just going to substitute them into my equation here. So what have I got? I've got ax equals, the xx component was alpha v. Actually, I'll take a component. Yeah, I'll write it all in. Nx plus, and then this one was xy. Xy was this one here, which was beta v n y. I think that's right. We've got gamma equals x. Yeah, that's a plus. That's a plus beta because it's this row here that I'm working with. There we go. That's nice. And y, the y component of the acceleration, is what? That's y, x, y. So that's a beta v n x, just substituting in this line here, plus, and because of the traceless condition, that's going to be a minus alpha times v times ny, where v was the oscillating component, which was, let me get it right from here, minus omega squared over 2 minus omega squared over 2 times the real part of this lot here, times the real part of e to the I minus omega t plus omega z, close one bracket. So that's the oscillating component. Well, that's nice. That's nice, isn't it? I'm going to stop there. This has taken me longer than I expected. So I'm going to stop here, and what I'm going to do is draw some graphs in the next screencast. Stop.